Today, for the very first time on this channel, we are talking about an engine coming from China. A mass-produced gasoline engine built and developed in China by automotive giant Geely. An engine that achieves an absolutely incredible, mind-blowing thermal efficiency of 48.41%. No, it's not fake news. That's the actual verified thermal efficiency. Of course, with this kind of crazy thermal efficiency, it's not surprising that this engine also powers the current Guinness World Record holder for the most fuel-efficient mass-produced car. To put the thermal efficiency into perspective, allow me to say that Toyota has managed 41% with their latest generation of dynamic force engines, whereas Nissan has managed 42% with their e-power system, but here the engine only ever acts as a generator, whereas both Toyota's and Geely's engines, they do power the wheels. Improving engine efficiency beyond 40% is an area of ridiculously diminishing returns. Achieving a 1% improvement in this zone is already massive, yet Geely somehow managed to outperform Toyota by an incredible 7.4%. And in this video, we're going to learn exactly how that was done. So let's start with the basics, with the heart of the engine anatomy, the bore and stroke. Unfortunately, Geely has not published the exact bore and stroke, but we can calculate it because they have published the engine displacement, the number of cylinders, and the stroke-to-bore ratio, which is 1.39 to 1. So the stroke is 39% larger than the bore. And if we do the calculations, we're going to get that we have a bore of 70 millimeters and a stroke of 97.4 millimeters. As you can see, this is a ridiculously undersquare engine, probably the most undersquare mass-produced gasoline engine I have ever seen. Here's a table showing the bore and stroke values of various famous as well as some of the most undersquare engines out there. As you can see, the Geely 1.5 I-HEV engine is in a league of its own. Now, let's put the Geely side by side with an old-school muscle car engine to better illustrate and understand the benefits and the reasons behind such an undersquare design. One of the reasons is that perfectly sealing piston rings, they unfortunately don't exist. There's always a tiny little bit of blow-by. Something always gets passed, and that little something negatively impacts your emissions. So the smaller your bore, the smaller the overall area over which blow-by can occur in the first place. And this then reduces your overall emissions footprint. This is why engines in general have been getting more and more undersquare over the past 20 years or so. The other reason to have a very small bore and a very long stroke is that such an anatomy favors efficiency. An oversquare engine like our Ford 289 here has a big bore. And a big bore means that we can stuff a lot of air and fuel into the cylinder and deliver a big punch. Because our stroke is kind of short compared to our bore, it means that our piston doesn't have to cover a long distance within a given period of time, which means that it doesn't have to travel too fast. And that makes it possible to rev higher. So not only can we deliver a big punch, we can also deliver it more frequently because we can rev higher. The result is a powerful, fun engine full of character. In an extremely undersquare design, we take a totally opposite approach. We have a small bore, which means that we are limited in the amount of air and fuel we can pack in the cylinder. We are delivering a small punch. At the same time, the very long stroke means that we'll be able to extract more of the energy off our small punch because our piston has a longer distance to cover while traveling downward and extracting energy. But because the stroke is longer, the piston must travel faster to cover it, which is why we can't rev as high, because at some point piston speeds become so high that the engine destroys itself. But with an undersquare engine, we usually don't even want to rev high because our priority isn't making power. It's extracting all the energy from our little punches. All else being equal, undersquare engines are usually more fuel efficient. An engine usually injects fuel from only one point in the combustion chamber. A larger bore results in a much larger chamber, which means that distributing fuel equally throughout it is more difficult. The result is an increased potential for unburned fuel and suboptimal combustion at reduced load, airspeed, and RPM. This, of course, negatively impacts both fuel efficiency and emissions. A smaller bore means that we have a much smaller area over which we need to distribute fuel, which means that we have better control over air and fuel mixing, and this leads not only to less unburned fuel, but to less overall fuel being required to achieve optimal combustion. Being super undersquare alone is definitely not enough to achieve that impressive thermal efficiency. We also need cringy branding. That's why this engine features something known as a fire tornado combustion system and a duckbill intake. All this really is an optimized intake anatomy, which improves air velocity as well as air tumbling. All of this then leads to better air and fuel mixing and an optimized combustion. To further optimize the combustion, injection pressure has been raised to 500 bar, which of course improves fuel vaporization, and then to squeeze out every last bit of energy from our super optimized air and fuel mixture, we have a 15.5 to 1 compression ratio. This is now pretty much the compression ratio of a modern passenger vehicle diesel engine in a mass-produced gasoline engine. On top of all of that, we have laser-clad valve seats, which means that the valve seats are now directly deposited, they're fused onto the cylinder head instead of being pressed in like traditional valve seats. This not only improves cooling, it also gives more freedom when it comes to intake port design and placement, and it is what makes that fire tornado duckbill thing possible in the first place. And we also have advanced surface treatment and machining techniques along with DLC or diamond-like coatings on many moving parts and surfaces for an overall impressive reduction of friction. And there you have it, 48.41% thermal efficiency. Well, at least according to the press release. If you have been following engine development in the last, 10 years, you've probably noticed that this engine is about as innovative as a brick. Let's compare it directly to a Toyota dynamicforce engine to illustrate my point. Both the Geely and the Toyota are undersquare, the Geely even more so. Both have incredibly high compression ratios, the Geely even more so. What Geely calls fire tornado and duckbill, Toyota calls an optimized intake port edge and shape. Less silly marketing terminology, but the exact same effect. Laser-clad valve seats are also present on both engines, as are diamond-like coatings and advanced surface machining and treatments. What Geely achieves with 500 bars of direct injection pressure, Toyota achieves with a combination of direct and port injection. All of these technologies can be found on several different engines from many different global manufacturers, and they most certainly do not explain an efficiency difference of 7.4%. The slightly higher compression ratio and the more undersquare anatomy, they account for maybe somewhere around 1%. That's it. So where does the rest come from? It comes from this, a deep Miller cycle. That's the key thing. Unfortunately, manufacturers and journalists have been throwing around the words Atkinson and Miller to the point that the difference between the two has been blurred. Toyota hybrid engines are Atkinson cycle engines. An Atkinson cycle simply means that the combustion or expansion stroke is longer than the compression stroke. We spend more time harnessing the energy of combustion than consuming it on compression. The longer the expansion stroke in relation to the compression stroke, the more energy of combustion will be harnessed and the higher the thermal efficiency will be. The inventor of the Atkinson cycle, James Atkinson, achieved this using a complex system of rods and linkages. Today, the Atkinson cycle is achieved more elegantly using valve timing. We simply delay the closing of the intake valves. Instead of closing the intake valve at the beginning of the compression stroke, we leave it open. If the intake valve is open, we of course can't compress the air-fuel mixture. Instead, we push some of it past the intake valve back into the intake port. The late closing of the intake valve simply means that the effective compression begins later. The result is that now we have an expansion stroke that is longer than the compression stroke, which leads to a more efficient engine. However, there's a limit to this. There's a limit to how late you can close the intake valve, how late you can begin the actual compression stroke, because the later you begin, the less air and fuel you can realistically store inside the cylinder. The less air and fuel you have, the less powerful your combustion. This is why Atkinson engines are noticeably less powerful and less responsive compared to conventional or Otto cycle engines. But they make great candidates for hybridization because the electric motors, they fill in the performance gaps of the Atkinson while maintaining the superior efficiency. Now, a Miller cycle is really just an Atkinson cycle engine together with a supercharger or a turbocharger, which is used to make up for the lack or the reduced amount of air and fuel inside the cylinder. Unfortunately, manufacturers and journalists and others have been calling Atkinson cycle engines that don't feature any kind of forced induction, they call them Miller cycle engines. The 1.5-liter Geely engine is one such engine. When I first read the words Miller cycle engine, I suspected some sort of maybe electric compressor or something, but no, there isn't any traces of that according to all the information currently available. It is a naturally aspirated engine. So it is a 1.5 Miller/Atkinson. That's not important, the word, whether we use Miller or Atkinson. The important word here is deep. That's what they mention. Deep Miller cycle. This is where the efficiency improvement comes from. It comes from the depth of the Miller/Atkinson cycle. It comes from the timing. It comes from the fact of very late intake valve closing. It comes from here because that's the only place where it can come from. Modern Atkinson engines close the intake valve once about 20 to 30% of the physical compression stroke has been completed. But if we were to go deeper into the stroke and close it even later, at let's say 50 or even 60% of the stroke, we could dramatically improve efficiency and reach 48.41%. The negative consequence is that such an engine would be pretty gutless and unusable without the assistance of electric motors. The main difference between the Toyota and the Geely is that in the case of Toyota, the engine is the primary mover and the electric motor assists the engine. In the Geely, it's the other way around. The electric motor is the primary mover and the engine assists the motor. Toyota hybrids are electrified combustion vehicles, as are pretty much all other hybrids from major global manufacturers. The Geely is an enginified EV. Toyota's engines and the engines of other major European, Japanese, and US manufacturers work both as ICE only and as hybrids. The thermal efficiency difference between a Toyota engine used in a hybrid vehicle and the same engine as ICE only without the assistance of electric motors is only 1%. The Geely record-breaking engine is a hybrid-only engine. It would be unusable without the assistance of electric motors. So really what Geely has done here is that they made the world's most efficient mass-produced gasoline engine by increasing the size of the electric motors and the batteries. This made it possible to use an extremely deep Miller, aka Atkinson cycle engine. It made it possible to close the intake valves very, very late. Doing so on a vehicle with smaller motors and batteries would actually lead to unacceptable performance. So although the thermal efficiency makes for great news headlines, there is realistically zero new or revolutionary combustion engineering in this engine. And it is simply a different approach to hybrids and an engine that could have been made by a Japanese, European, or US manufacturer had they chosen to take such an approach to hybrids. However, it is still an important achievement for a Chinese manufacturer because, realistically, Chinese manufacturers are novices in engine development when compared to European, Japanese, or US manufacturers which have a longer track record and experience of engine development. And it's a showcase of how apparently Chinese manufacturers have fully caught up with key global players when it comes to engine technology. But here's an interesting question. Why haven't any of the non-Chinese manufacturers adopted this electric-centric approach to hybrids? Well, one of the reasons why Chinese manufacturers are doing it is that they recently started backpedaling from full EVs a bit. It's not entirely clear why. Maybe the economies of ever larger, ever heavier batteries didn't really make sense. Maybe battery technology didn't progress as fast as they hoped. I really don't know. What I do know is that because of this, they are starting from a completely different end of the spectrum. What they're doing is that they're actually combustionizing their EVs. And that's something that none of the European, Japanese, or US manufacturers have ever done. But maybe they should. Maybe this is the better approach. Maybe an electric-centric hybrid makes more sense because isn't it more efficient? Isn't it more efficient because it spends more time in EV-only mode with the engine shut off? Yes, it is more efficient in some scenarios where it's capable of achieving better peak efficiency. But it pays for it by being less versatile and even being disappointing in some other scenarios. As many buyers of Chinese hybrids and plug-in hybrids with very small underpowered engines have noted, when the batteries are completely depleted, there's a very sudden, very noticeable drop in vehicle performance and power. Yes, a larger battery isn't as easy to deplete, but it's also not hard to find a continuous uphill section on the highway or a long uphill mountain road or whatever. In this scenario, the very small lethargic engine simply becomes unable to both power the wheels and charge the batteries, and you get a very noticeable, irritating loss of power. Of course, Geely is fully aware of this, and they decided to solve the problem with the modern fix for everything: AI. The cars, they feature something Geely calls an AI power cloud system, I believe. Basically, what it does is that it uses AI to micromanage the state of charge of the batteries and the electricity and all of that. Basically, what it does is that based on your location and your destination, it's going to anticipate when you're going to hit an uphill, continuous uphill. So it's going to instruct the engine to charge the batteries while it still can on flat ground before the uphill, so that you don't run out of batteries during the uphill and you don't get the annoying power drop. Now, before we end things, I'd like to say that today's video has been brought to you by Onshape. These engine animations that you have seen in the video have been made entirely in Onshape by me, and as I've come to expect, it's been an absolute breeze to make and animate them. But ease of use is just one of the benefits of Onshape. It is also 100% browser-based, something I really like because it means that you can open all of your saved work from anywhere in the world at any time from any device. It makes also the hardware capabilities of your device completely irrelevant. You can run Onshape on anything, and it completely eliminates crashes, updates, lost work, and none of that archaic stuff anymore. And it's great even if you're a complete beginner, because Onshape has a giant public library of all kinds of files so that you can use, modify, experiment on, and learn from. And they also have a lot of really well-made instructional videos that cover everything from the most basic stuff to very advanced design techniques. We live in a day and age where it's honestly getting harder and harder to imagine product design, prototyping, or even DIY without a 3D CAD software. And Onshape combines user-friendliness with an extremely potent toolbox and maximum convenience, which, at least in my opinion, makes it the go-to CAD software for pretty much anything. If you want to give it a try yourself, check out the links in the description and the pinned comment. So there you have it, the world's most efficient gasoline mass-produced engine, brought to you by bigger batteries and motors. As always, thanks a lot for watching. I'll be seeing you soon with more fun and useful stuff on the D4A channel.